On August 10, a Chinese company called LandSpace is targeting a launch that could change the rhythm of the commercial space race. Its reusable rocket, Zhuque-3, is being prepared for a historic attempt: rise to orbit, release its payload, and then return its first stage for a controlled landing. That sounds familiar. SpaceX has made booster recovery look almost routine. But every new company that attempts it is testing a different machine, a different business model, and a different idea of how quickly humanity can make spaceflight reusable. In this episode, we will follow the physics, engineering, and strategic meaning of LandSpace's planned flight. We will also separate what is genuinely new from what is simply difficult, because in rocketry, the difference between a demonstration and a dependable system is measured in many successful flights. The story begins with the basic problem of reaching orbit. A rocket does not merely have to go upward. It must accelerate sideways fast enough to keep falling around Earth instead of falling back onto it. At low Earth orbit, that sideways speed is roughly 7.8 kilometers per second. Once gravity losses, aerodynamic drag, steering, and the need for fuel reserves are included, the vehicle must produce a change in velocity of more than 9 kilometers per second. This is why rockets are mostly propellant tanks. The rocket equation is unforgiving. Every kilogram of structure, engine, landing gear, or heat protection must be lifted by propellant, and then more propellant is needed to accelerate the propellant that remains. Traditional rockets accepted that most of the vehicle would be discarded. Reusability changes the calculation. Instead of throwing away engines and tanks after one trip, the operator can spread their cost across many launches, provided inspection and refurbishment do not erase the savings. A reusable booster follows a carefully choreographed path. During ascent, its engines push the vehicle toward orbit. When the first stage separates, it is still traveling at tremendous speed, high above the atmosphere, and usually in the wrong direction for a simple descent. The stage must perform a boost-back maneuver, using a controlled engine burn to shape its trajectory. It then falls through the atmosphere, where aerodynamic forces can heat its surface and also provide a way to steer. Near the landing zone, the booster performs a landing burn. The timing must be precise. Too early, and the vehicle runs out of fuel before reaching the ground. Too late, and it cannot slow down before impact. LandSpace Zhuque-3 is designed around this same broad philosophy, a two-stage orbital rocket with a first stage intended to return. Its development reflects a larger shift in China's launch industry, from a system dominated by government missions toward a crowded field of commercial companies. The company is not starting from zero. LandSpace has already flown its Zhuque-2 rocket, a vehicle known for becoming the first methane-fueled rocket to reach orbit. That achievement mattered because methane offers a promising balance for reuse. It burns relatively cleanly, can support high-performance engines, and can be produced from resources available on some future worlds. But reaching orbit once is not the same as recovering a booster. A reusable stage must survive vibration, engine operation, separation, atmospheric entry, and landing. It must also be manufactured consistently enough that every flight behaves like the last one. The planned Zhuque-3 mission is therefore more than a launch. It is a full-scale experiment in operations. The vehicle will test how its engines throttle, how its guidance system responds to changing winds, how its tanks handle the stresses of flight, and how its thermal protection performs during descent. The most visually dramatic part may be the landing. From the ground, a returning booster appears to reverse its fall and settle onto a pad. In reality, the computer is continuously estimating position, velocity, atmospheric conditions, and remaining propellant while commanding engines in fractions of a second. A landing can fail without a single spectacular hardware break. A small navigation error can move the vehicle beyond the pad. A valve can respond slightly too slowly. A gust of wind can change the final approach. Reusable rocketry is a system problem, not just an engine problem. The choice of methane is also important. Kerosene has powered many successful orbital rockets, but soot and combustion residues can complicate repeated use. Methane can reduce some of those deposits and may enable faster turnaround, although it creates its own challenges in cryogenic storage, combustion stability, and engine design. Zhuque-3 is expected to use methane and liquid oxygen, both stored at very low temperatures. The propellants must remain stable through loading, countdown, launch, and stage operations. Plumbing must prevent leaks, pumps must operate under extreme conditions, and engines must start reliably every time. This is where the commercial space race becomes a race in manufacturing. A prototype can be assembled slowly, inspected constantly, and treated as unique. A useful launch service needs factories, suppliers, test stands, software teams, recovery crews, and customers who can plan around a launch schedule. LandSpace's target date is attracting attention because it follows a series of rapid developments across the global industry. SpaceX is launching Starlink satellites at an extraordinary cadence, while other companies are trying to develop reusable vehicles of their own. India, Japan, Europe, and the United States are all pursuing different approaches to lower launch costs. Some are building reusable first stages. Others are focusing on small rockets, recoverable engines, or spacecraft that can be serviced in orbit. China's commercial launch companies are entering this environment with strong domestic demand. Communications satellites, remote sensing, navigation, and scientific spacecraft all need access to orbit. A successful reusable launcher could give customers more scheduling options and help reduce the price of each kilogram delivered to space. Yet the word successful needs a careful definition. If Zhuque-3 reaches orbit but the booster is not recovered, the mission could still provide valuable data. If the stage lands but requires months of repair, that is still progress, but not the same progress as rapid, reliable reuse. The strongest test will come later. Can the recovered hardware fly again, and can it fly again without a massive rebuild? Spaceflight history is full of vehicles that worked once. The real revolution is creating a machine that works repeatedly. There is also a geopolitical dimension. Reusable rockets are not only commercial transportation. They demonstrate advanced propulsion, guidance, materials, and industrial coordination. They can support national space programs and expand a country's ability to place satellites into orbit quickly. That does not mean every launch should be interpreted as a military signal. Most spacecraft are civilian or commercial. But launch capacity is strategic infrastructure, much like ports, aircraft manufacturing, and communications networks on Earth. For observers, the mission will offer several clues. Watch the ascent profile and listen for whether the engines operate smoothly through throttling events. Watch stage separation, because the booster must stabilize itself immediately after leaving the upper stage. During descent, the key moments are the entry burn, atmospheric flight, and landing burn. The vehicle may use grid fins or other aerodynamic controls to steer through the upper atmosphere, then rely primarily on engine thrust during the final approach. A successful landing will not prove that China has copied another country's exact playbook. It will show that the underlying physics can be converted into a second operational pathway. Different launch sites, regulations, supply chains, and mission requirements may lead to different designs. And a failure would not end the story. Early reusable rockets are built to reveal their weaknesses. Engineers will examine telemetry, recover fragments if possible, and update software or hardware. The question is not whether development is perfectly smooth, but whether each flight turns uncertainty into evidence. There is a quiet irony in all this. Reusable rocketry is often presented as a dramatic leap toward the future, but its progress depends on repetitive work, welds checked, engines fired on test stands, sensors calibrated, landing algorithms simulated, and procedures rewritten after every anomaly. The spectacle is the launch. The revolution is the logistics behind it. If Zhuque-3 completes its planned flight and returns its first stage, the achievement will add a new name to the short list of organizations that have demonstrated orbital booster recovery. More importantly, it will make reuse feel less like a single company exception and more like the emerging standard of serious launch engineering. That could affect everything above Earth. Lower launch costs make satellite constellations easier to expand. More frequent flights create new opportunities for science and Earth observation. Future missions may launch spare parts, fuel depots, or technology demonstrations that would once have been considered too expensive. But cheaper access also creates new responsibilities. More spacecraft mean more congestion. Operators must track debris, coordinate traffic, and design satellites that can be safely removed from orbit. Reusable rockets solve one part of the space economy while making good orbital stewardship even more important. The long-term question is not who lands the first booster on a given day. It is who can build a complete, dependable transportation network. That network must launch on time, recover hardware safely, refurbish it quickly, and protect the orbital environment where every customer operates. LandSpace's upcoming attempt is a snapshot of that larger transition. It is a test of methane propulsion, reusable guidance, commercial manufacturing, and national ambition all at once. For decades, a rocket launch ended when the vehicle disappeared into the sky. Now, the most important part may begin after separation, when an empty stage turns around, dives back through the atmosphere, and tries to land with enough precision to fly again. Whether Zhuque-3 succeeds completely, partially, or not at all, its flight will teach us something about how the next era of spaceflight is being built. Not in science fiction, and not in a distant century, but through machines being tested one launch at a time. The future of space may not arrive as one giant leap. It may arrive as a booster returning to a landing pad, followed by another, and then another, until reuse is no longer a headline but simply how orbit works. This is the quiet cosmos. Subscribe for more calm,